My good friends, welcome to my online class. My name is Tete Jacob C. Richard. Today our discussion on calculus of several variables will be on surface integral leading to polar integration. I have a video where I introduce you to surface integration problem that may lead to a normal integration that involve integration using the simple principles of integration, using integration by part, then using integration by substitution. At times, our surface integral problem may not lead to any of these integrals. Thus, using simple integration rule, using integration by part, then using integration by substitution. In that case, polar integration steps in to hold the situation handy. So, before the video ends, I will take you through how to switch from normal integration to polar integration. Then I will tell you a surface integration problem that involve polar integration. Then we take some sample problems and find solutions to them. This will be a very interesting engagement, so please watch the video till the end. So, when our surface integration problem lead to polar integration, there is a need for you to switch from the normal integration to polar integration. What tools that are necessary to switch? So let's say this is our Cartesian plane involving a circle. Since a circle also involves polar integration for that matter. So let's say this is the x-axis, the y-axis, and r. Remember, the r is the radius. Any line drawn from the center of the circle to the circumference is the radius. Then using Pythagoras theorem, we can say r squared is equal to x squared plus y squared. Thus, x squared plus y squared is equal to r squared, where r is the radius of a circle. So if we have any equation, for instance, x squared plus y squared equal to 25, we can rewrite this equation as x squared plus y squared equal to 5 squared. Then comparing it to x squared plus y squared equal to r squared, we can say the radius of that circle of this equation is 5. Then we can also say that the radius starts from 0 to when it is 5. So the radius is 0,5. Also, remember that we said that the total angle of a complete circle is 360 degrees. So we can say that the angle starts from 0 degrees to 360 degrees. So we can say the value of theta is also from 0 degrees to 2 pi degrees. And 2 pi is the same as 360. Remember, pi is 180 pi is equal to 180 in radius. If you remember that very well. Also, there is a very important rule that makes it to switch. We need to find the value of x and y in terms of theta. And using the trig identities, so, ka, toi. How do we find the relationship between the theta radius and x and y? So remember, this is our opposite and this is our adjacent. And the radius represents the hypotenuse. So if we want the adjacent over hypotenuse, adjacent, that's cos. So we can say cos theta is equal to x over r. Then we can say our x is equal to r cos theta. That's when we cross multiply both sides. Also, we can also say sin theta is equal to y over r from the circle. Then our y is equal to r sin theta. I hope you get that. So, in switching, we will know that our s is r cos theta and our y is r sin theta. Also, the values of r or the values of the radius will be determined from the equation of the circle that involve the switch. Then also, the values of theta will be from 0 degrees to 360 degrees. I hope you know that. Also, if you really watch that video where we have surface integration problem that lead to normal integration, we say that our surface integral is giving us double integral of a function depending on x, y, z ds, where z is also a function depending on x and y, if you recollect that. And we said that our ds is equal to the square root of dg over dx squared plus dg over dy squared plus 1 dx dy, if you recollect very well. In this case, we can say our double integral of f of x, y, and z, where z is also another function depending on x and y, the square root of, in place of dx, we substitute this, dg over dx all square plus dg over dy all square plus 1 dx dy. So, any place we are going to see x here, we'll substitute r cos theta. In any place we see y, we substitute r sin theta. What of the dx dy? Our dx dy will be giving us r dr d theta. So please remember, there is a proof for this. I indulge you to check it out. So dx dy in our normal integral problem, switching to polar integration, will become r dr d theta. Then after we substitute that, you realize that our s is r cos theta, y is r sin theta, and dx dy becomes r dr d theta. Dx dy becomes r dr d theta. Then you have switched everything from x and y plane to polar, which involve the radius of the circle and the angle theta. So now we take some sample questions and see how surface integral problems can be switched to polar integration to solve the problem. So let's look at our first one. They say evaluate the surface integral, double integral ds, where a is the portion of the graph of the function z is equal to a function g depending on x and y equal to 16 minus x squared minus y squared bounded below the xy plane. So, if you meet a problem, how will you know that the problem involves a switch to polar integration? You realize that the limit point of x and y will not be given in the question. So you see that the ones we did earlier, you see that the limit point of x and y are given. But this one, the limit point is of x and y are not given. Then immediately, you know that the problem will be switched from normal integration to polar integration. Very, very important. So now, you realize that the function f is not given there. It's given, but you realize that there are no variables. So it means that the function f, depending on x, y, and z, is equal to 1 for this case. So we can say the double integral f of x, y, and z ds will be equal to, remember, will be equal to the double integral f of x, y, and z is 1. So 1, and ds is equal to the square root of dg over dx all square plus dg over dy all square plus 1 dx dy. You know this very well. And what's our g? Our function g is giving us 16 minus x squared minus y squared. So dg over dx is just the partial differentiation of this function with respect to x. Then dg over dy is the partial differentiation of this function with respect to y. So we can say our dg over dx will be equal to, this is constant, so 0, this will be minus 2x, and this will also be 0. Then our partial differentiation of the function g with respect to y will be equal to, this will be 0 since it's constant, this is 0 since it will be constant, then this will be minus 2y. So, in substituting it into this, we can say our double integral, the square root of, in place of dg over ds, we put negative 2x all square plus negative 2y all square plus 1 dx dy. So we can simplify simplify this one as the square root of negative 2x squared will be 4x squared. The negative 2y squared will be 4y squared plus 1 dx dy. Now, look at this problem. Do you have any clue how to solve this? Can you use simple integration problem to solve this? Can you use integration by substitution? Or you use integration by parts? None of those integrations will help solve this problem. Then immediately, there is a need to switch to polar integration. Remember, the limiting points are not even also given. So how will you solve that? So there is the need to switch to polar integration. So how do we switch to polar integration? So there is a need to switch. Immediately identify that it involves polar integration. And remember, I drew this earlier on. So the g function becomes the equation of the circle. Very, very important. Immediately, you must equate that to 0. So we say 16 minus x squared minus y squared should be equated to 0. And you can say minus x squared minus y squared equal to minus 16. X squared plus y squared will be equal to 16, multiplying through by negative 1. Then you can say x squared plus y squared is equal to 4 squared. Comparing it to x squared from this x squared plus y squared equal to r squared using Pythagoras theory, we can say the radius of our circle is 4. So the limiting point of the radius is spanning from 0 to 4. And that of theta, remember, we span from 0 to pi. That's from when when theta is 0 to when theta is having a complete circle. And a complete circle is 360 degrees, and that's 2 pi in radian. Also, there is a need to find the values of x and y in terms of theta and pi. And we say that our x, if you remember very well, our x will be equal to r cos theta, and y will be equal to r sin theta. And since we know x and y, and we know the limiting point of r and theta, we also know that our dx dy from there, dx dy is equal to r dr d theta, if you recollect very well. So in substituting all these things, knowing that the limiting point for r is 0 to 4, and that of theta is from 0 to 2 pi, and our dx dy is equal to r dr d theta, we'll substitute that here. And also, our x is equal to r cos theta, y is equal to r sin theta. We substitute, then we switch to polar integration. So now let's substitute. So we have double integral the square root of 4x squared. So we have 4 bracket x now is r cos theta. So r cos theta square, then plus 4, our y is r sin theta square plus 1. Remember the square root affect the 1. And our dx dy is equal to r dr d theta. So what do we have? We have double integral the square root of 4r squared cos square theta, when we square this, plus 4r squared sin square theta plus 1 r dr d theta. So we have double integral. Remember the limiting point of r and theta are also here. So we'll finally substitute them. So we have the square root of, now 4r squared is common to them, we can bring it out. So we have 4r squared bracket cos square theta plus sin square theta plus 1 r dr d theta. So we have double integral the square root of 4r squared. Cos square theta plus sin square theta is nothing but 1. You know that. So in place of that, we substitute 1. So we say times 1 plus 1, then r dr d theta. So when we simplify further, we have double integral the square root of 4r squared plus 1 r dr d theta. So we can now substitute the limiting point for r and theta. Remember, dr comes first, so it will be here. Then the theta comes second. Then that one will take this. So we have the integral spanning from 0 to 2 pi, and the integral spanning from 0 to 4, the square root of 4r squared plus 1 r dr d theta. So immediately you switch, you see that this can involve in a simple integration problem to solve. Since when we differentiate 4r squared, we'll get 8r. R pop up here, we can use integration by part to deal with that of the r. So now we'll solve that by integration by part, then we take it from there. So in solving that by integration by substitution, we can say we should let u to be equal to 4r squared plus 1. That's, this can be written as double integral spanning from 0 to 2 pi and spanning from 0 to 4 of 4r squared plus 1, all exponent half. Remember that. Then r dr d theta. So we can find du over dr. Du over dr will be equal to 8r. When we multiply both sides by dr, we can say our du is equal to 8r dr. Now divide both sides by 8. Our du over 8 will be equal to r dr. Also, because it involves a limit integration that involves integration by substitution, we need to find the corresponding value of u. So when r is 4, what will be u? U will be equal to 4 into bracket 4 square plus 1. That's substituting 4 into this place. 4 square is 16. 16 times 4 will be 64 plus 1 will be 65. Then when r is 0, our u will be equal to 4 times 0 square plus 1. 0 square is 0 times 4 is 0 plus 1 is 1. So the corresponding value of r in u will be 65, spanning from 1 to 65. Then we can change this our integration problem to look like this. That's double integral spanning from 0 to 2 pi and spanning from, now the limiting point will be from 1 to 65 for the u. Then 4r squared plus 1 is u. So we say u exponent half. Then our r dr is du over 8. R dr is du over 8. So you can say du over 8 then d theta. And this is fraction 1 over 8. I can bring it out. So in bringing the 1 over 8 out, I can have 1 over 8, since it's constant. The integral spanning from 0 to 2 pi and integral spanning from 1 to 65, u exponent half du d theta. So now we integrate this with respect to u. So we have 1 over 8. Integral spanning from 0 to 2 pi. Then when we integrate this, remember simple integration rules. U exponent half, we'll add 1. That becomes 3 over 2. So 3 out of 2 over 3 out of 2. Spanning from 1 to 65, then d theta. We have integrated the du. So please check out my videos on double integration on YouTube. So we can have 1 over 8 integral spanning from 0 to 2 pi, then this can be written as, that's we multiply, so we reciprocate 2 over 3 u exponent 3 over 2 spanning from 1 to 65 d theta. Since this is fraction, I can bring it out. I'll have 1 over 8 times 2 over 3 integral spanning from 0 to 2 pi of u exponent 3 over 2 from 1 to 65 d theta. So in solving this further, 2 divide 8 4 times 3 will be 1 over 12. So we have 1 over 12 integral sine from 0 to 2 pi. Then now we can substitute this. So we say 65 exponent 3 over 2 minus 1 exponent 3 over 2 d theta. Remember, a 1 exponent, any number will be 1. So we say this is equal to 1 over 12 integral spanning from 0 to 2 pi 65 exponent 3 over 2 minus 1 d theta. I hope you get that. Since this is constant, I can bring it out. So I will have 1 over 12 times 65 exponent 3 over 2 minus 1 integral spanning from 0 to 2 pi d theta. Remember, this is 1, and when we integrate 1, we'll get theta. So we say this is 1 over 12 times 65 exponent 3 over 2 minus 1. The integral of this will be theta spanning from 0 to 2 pi. So we now substitute that. So we have 65 exponent 3 over 2 minus 1 all over 12. Then 2 pi minus 0. Remember how to substitute. In place of pi, we just put 2. In place of theta, we put 2 pi minus 0. I hope you know how to solve finite integrations. So I have 65 exponent 3 over 2 minus 1 all over 12 times 2 pi. So 2 going to 12 6 times. So we can say pi into bracket 65 exponent 3 over 2 minus 1 all over 6. So we know pi is 3.142. We just find 65 exponent 3 over 2, then we evaluate. So pi is 3.142, then 65 exponent 3 over 2 will be 524.05, then minus 1, then divided by our 6. 3.142 divided by 6 will be 0.5237, and 1 minus 524.05 will be 523.05. When we multiply 523.05 by 0.5237, we'll get 273.9, close to correct to 1 decimal place. Then this becomes our surface area. I hope you get that. When you practice more of this, you understand. We'll solve one more example on this so that you'll be abreast with the concept. So we'll solve our second problem on this. They say evaluate the surface integral, double integral of a function x squared plus y squared plus z dx, where x is the portion of the graph of the function z equal to 4 minus x squared minus y squared, bounded below the xy plane. So please remember to subscribe to my YouTube channel so that YouTube can promote my videos and I can record more mathematical content for you. Now pause the video and try and see if you can solve the question on the board. After that, you compare your answers with mine. So let's see this. Now we know that the surface integral is given a double integral of a function depending on x, y, and z dx. And remember, the function of x, y, and z is given as x squared plus y squared plus z. We can say this is equal to the double integral of x squared plus y squared plus z dx. Our z is given to be 4 minus x squared minus y squared. And remember, it's also a function g depending on x and y. Very, very important. So we can substitute z. So we can have our double integral. Please remember, this is double integral. We can have double integral of x squared plus y squared. In place of z, we substitute plus 4 minus x squared minus y squared. And remember, ds is the square root of dg over dx all square plus dg over dy all square plus 1 dx dy. If you remember very well. Look at this. X square minus x square will be 0. Y square minus y square will be 0. Then we'll have double integral of what is left there is 4. Integral of dg over dx all square plus dg over dy all square plus 1 dx dy. So we know our function g is the same as z if you watch the video from the beginning. So our g, depending on x and y, is equal to 4 minus x squared minus y squared. So we find the g over there. That's the partial differentiation of that function with respect to x. The partial differentiation of the function with respect to y. Then we substitute. So we can say our dg over dx will be equal to the partial differentiation of this function with respect to x, we just minus 2x. Then dg over dy, the partial differentiation of this function with respect to y, we just minus 2y. Now we can substitute. So we have double integral of 4, the square root of, I'm just substituting that into this. So we have 4 minus 2x all square plus minus 2y all square plus 1 dx dy. Since 4 is constant, I can bring it out. So I have 4 double integral of the square root of, this will give me 4x squared plus 4y squared plus 1 dx dy. So you see that there is no, you can't solve this integration problem using simple integration rule. Neither can you solve using integration by part, and you can't solve using integration by substitution. You need to shift to polar. And remember, in shifting to polar, we'll have our equation of the circle to be this. And that circle may look like this. Well, we'll have our x and y plane, x, y, and theta, then our r. And remember, we said that our x will be equal to r cos theta if you solve, and our y will be equal to r sin theta if you recollect very well. And also, since our equation of the curve is 4 minus x squared minus y squared, we can just equate that to 0. So we know that r stands from 0 to a certain value. What is that value? Our minus x squared minus y squared will be equal to minus 4. So our x squared plus y squared will be equal to 4. So we can say x squared plus y squared equal to 2 squared. In comparing that to this, where r squared is equal to x squared plus y squared, using Pythagoras theory, you can say x squared plus y squared is equal to r squared. Then our r, when you compare, is 2. And we can say the limiting point of the radius of the circle starts from 0 to 2. And remember, since theta is a complete circle, it will be from 0 to 2 pi, if you recall it very well. So now we can just substitute to this our integration problem to switch from the normal integration that we know to polar integration. So in switching, we can say for the double integral, so let me substitute the limiting point at once of theta will be 0 to 2 pi, and of the radius will be from 0 to 2. Then we'll have the square root of, in place of x, we substitute r cos theta. In place of y, we substitute r sin theta. And also remember our dx dy will be equal to r dr d theta. So we substitute all the necessary things, then we pick it from there. So we have 4 brackets r cos theta square plus 4 bracket r sin theta square plus 1. Then in place of dx dy, we substitute r dr d theta. So what do we have now? We have 4 integral spanning from 0 to 2 pi for theta, integral spanning from 0 to 2 for the radius. We have the square root of 4. This will give me r squared cos square theta plus 4r squared sin square theta. Then plus 1 r dr d theta. We polish further. We have 4 integral spanning from 0 to 2 pi, integral spanning from 0 to 2 of the square root of. Now 4r squared is common, we can bring it out. 4r squared will be left with cos square theta plus sin square theta. Then plus 1 r dr d theta. So remember, cos square theta plus sin square theta is nothing but 1. So in place of all this, it will be 1. So when we simplify further, we have 4 integral spanning from 0 to 2 pi for theta, integral spanning from 0 to 2 for the radius. The square root of 4, we said this is 1. So remember, we factor out 4r squared. So we have 4r squared, then times 1 plus 1 r dr d theta. So what we have? We have 4 integral spanning from 0 to 2 pi for theta, integral spanning from 0 to 2 for the radius. We have the square root of 4r squared plus 1 r dr d theta. So you see that now our integration problem can be solved with the familiar integrations that we know. If we differentiate 4r squared, we'll get 8r. R pop up. Then we can use integration by substitution again. And remember, this our problem can be written as 4, a double integral, spanning from 0 to 2 pi for theta, and spanning from 0 to 2 for the radius. We have 4r squared plus 1 exponent half r dr d theta. So we said we let our u to be equal to 4r squared plus 1. Then our du over dr will be equal to 8r. Or multiply both sides by dr, our du will be equal to 8r dr. We divide both sides by 8. We'll get du over 8 will be equal to r dr. Then, since we are switching, we must find, we are using integration by substitution. Remember, these are the values of r. We must find its corresponding value for the u. Very, very important. So we can say our u will be equal to, when r is 2, u will be what? 4 times 2 squared plus 1. 2 squared, remember, is 4. 4 times 4, 16 plus 1, that will be 17. Then when u is, r is 0, u will be equal to 4 times 0 squared plus 1. 0 squared is 0 times 4 will be 0 plus 1 will be 1. So in place of 0, we substitute 1. In place of 2, we substitute 17. In place of 4r squared, that's 4r squared plus 1, we substitute u. In place of r dr, we substitute the u over 8. So since we know this is 1 over 8, it's a constant, we can bring it out to multiply the 4. Our 4 times 1 over 8. Integral spanning from 0 to 2 pi for theta. Integral spanning from 1 to 17 for u. U exponent half du d theta. Now we can integrate this with respect to u. 4 times 1 over 8 will give me half. Integral spanning from 0 to 2 pi. Since we are going to integrate, we leave the integration for the u. when we integrate this, we have u exponent 3 over 2 over 3 over 2. Substituting from 1 to 17 d theta. So we can reciprocate this. That will become 2 over 3. So we have 1 over 2. Integral spanning from 0 to 2 pi. 2 over 3. U exponent 3 over 2. Substituting from 1 to 17 d theta. Since this is constant, we can bring it out. So we have half times 2 over 3. Integral spanning from 0 to 2 pi of u 3 exponent 2 substituting from 1 to 17 d theta. So I want to simplify this further. These two can divide out to. Then we'll be left with 1/3 outside. So 1/3 integral spanning from 0 to 2 pi. Then we can now substitute this. So we have u 17 exponent 3 over 2 minus 1 exponent 3 over 2 d theta. So we can have 1 over 3 integral spanning from 0 to 2 pi of 17 exponent 3 over 2. Then minus, this will be 1, then d theta. Since this is constant, I can bring it out. I'll have 1 over 3 times 17 exponent 3 over 2 minus 1. Integral spanning from 0 to 2 pi d theta. So if I integrate this with respect to theta, it will just be theta. So we have 1 over 3, 17 exponent 3 over 2 minus 1, then theta, substituting from 0 to 2 pi. So when we simplify further, we'll have 17 exponent 3 over 2 minus 1 all over 3. Then we can now substitute this. So we'll have 2 pi minus 0. Remember that. And this will give us 2 pi. So we can have 2 pi times 3 multiplying 70 exponent 3 over 2 minus 1. Remember, pi is 3.142. We find the value of 70 exponent 3 over 2. Then we take it from there. So the value of pi is 3.142. So 2 times that over 3. Then 70 exponent 3 over 2 will be 70.0928 minus our 1. When we subtract 1 from that, we get 69.0928. When 2 multiply 3.142, we get 6.284. When 6.284 multiply 69.0924, we get 434.1791 divided by 3. When 3 divide that, we get 144.7 our surface area. I hope you get this. Please play over the video and I know that you will get a concept. Before you sign out, remember to like my video, share my video, comment on the video. Your comment keep me going. And remember to subscribe to the YouTube channel if you are here to. Until we meet again, my name is Kepsi.